All right. So yesterday I was told Doc said he took you through the physical properties of rock, which you saw some basic properties of rock, such as the porosity, the permeability of the rock, the specific gravity, right? So today we are going to see phase relations of rocks, right? We are going to play with this physical properties of the rock, right? So which in other words called phase relations, right? The phase relations is as a result of, we are saying that in actual sense with soils, right, in a container, the soil will displace everything. Let's say we fill a container with soil such that it becomes contained, it becomes full of soil. Yet, we know that these soils are not 0% voids, right? There are spaces inside, and then we have some water also trapped in these waters, right? So we can say that, and in basic chemistry, we know that phase is when we transition from one point to another. So let's say I'm in my room, I'm in one phase. The moment I get out of my room and experience the air, I am in another phase. Sorry about that. So when we have soils contained in container like this, you know that it contains three matter there, which is solid, water, and air, right? You would say, I don't see any air spaces in the soil. How come are we saying that also the phases that we are playing with, we have air? You know that we have something that is called void, right? I don't think there is any soil that has zero voids, right? That one you'll be playing with deep buried igneous rocks, right? Well, we won't go there. All right, so these phase relations, we are going to see how much they play a role to affect the integrity of a rock, right? So soils and porous rock, right? So for this, we need the following, right? We need the mass. We need the mass. And then we are saying that it's a measure of the body's inertia, quantity, and matter, right? Mass that not change at different. Mass does not change at different places, right? The mass of a substance in Ghana is the same as the mass of a substance in UK. Mass is uniform and it does not change with places, except maybe you are affected by gravity. Even that one, you'll be playing with the weight and not the mass, right? Weight is a force of gravity acting on the body. Now, the inertia, when it is being acted on by a force to get some sort of power, right? Let me put in that sense. The mass, now we are putting some force on it, so it comes with a push, right? Some force, and that will be the weight, right? We are saying that it is dependent on the bodies or the place that we are, the gravity that is affecting. So the weight of a substance in Ghana or on Earth is not the same as the weight of a substance on the moon because it has different specific gravity, right? We are saying that the weight is the mass times gravity. It is dependent on the gravity that is working at that area, right? And then where the gym that we are going to assume in this context of phase relations is 9.81 meter per centimeter squared, right? And then we have another property we are going to play with, which is the density, how packed a substance is in a place or in a space, right? So that one brings about the density, which is the mass over the volume. And we have one other one, which is the unit weight, right? So unit weight is the weight over volume. Now, the density is how packed a substance is in a given volume, right? But unit weight is how much weight that is exerted on a volume of space, right? So that is unit weight. Now, when we play with these formulas, we are going to get unit weight, which is gamma, is equal to the density here, right? Because we can deduce that weight is equal to mass times gravity, and then the volume comes. So volume, mass over volume will change it into density times gravity, and then we have our unit weight, right? Unit weight is frequently used in geotechnical engineering than density in calculating the overburden pressure, right? So we'll be dealing more with the unit weight of the rocks, right? Because they affect structures more, all right? Now, units of unit weight and density. The SI unit of mass density is kilogram per cubic meter, right? So I want you to take note of the units, because when we are playing with those phase relations calculations, we want to keep our formulas uniform such that we can have a similar unit playing with all of them, and then we will not be escalating things, right? So the SI unit of force is Newton. Therefore, the unit of weight soil are typically kilonewton per meter cube. And you also want to keep this because most of the times they're going to be given in other forms just to trick us, and we will have to bring it back to kilonewton per meter cube, right? Okay. Now, you have to see the relationship between unit weight and density. The unit weight of soil is kilonewton per meter cube and can be obtained from densities of kilogram per cubic meter as this. Now, when we have gravity times density, then we'll be having unit weight, right? Now, because this 1,000 here is as a result of we are not playing with density of water in gram per cubic centimeter, right? But rather we are playing with kilogram per cubic meter, right? That is why we are saying that unit weight, which is in kilogram newton per meter cube, is equal to gram times the density in kg per meter cube all over 1,000, which is the unit weight of water, or in other words, the density of water, right? You are saying that the density of water varies slightly depending on the temperature at 4 degrees, right? So as you had, I didn't see his name, asking a question that the definition for specific gravity. So when you want to define specific gravity, then and we are using that it is the density of a substance over the density of water. And you have to bring this keyword that says that at 4 degrees Celsius, right? That is where the density of water is equal to 1,000 kilogram per cubic meter or 1 gram per cubic centimeter, right? Now, unit weight of water is 9.81. Unit weight of water is 9.81, right? In my earlier statement, I think I made a mistake by saying that the unit weight of water. No, the unit weight of water is 9.81, and this parameter, we are going to use it much in our calculations, all right? Now, soil phases, like I'm saying, the moment we move from one medium to another medium, we are switching phases. And I was given an analogy that when I am in my room, the moment I step out to encounter air, I have moved from one phase to the other. So the moment I dive into a swimming pool, I have moved from another medium to another. So I am switching phases, right? So soil deposits comprise of accumulated solid particles plus void spaces between the particles, right? We are saying that the void spaces are partially or completed filled with water or other liquids, right? And we are saying that the void spaces are not occupied by fluids. Are not occupied by fluids are, sorry, the void spaces that are not occupied by fluids are then occupied by air or other gases, right? So in a container where we have soil, all these phase relations or all these mediums are playing roles for us to have a natural soil, all right? And hence, soil deposits are referred to us as a three-phase system, that is a solid, a liquid, and gas. All right. Please, are there any questions? Is there anything I have to throw more light on?
Hello, sir.
All right. Ado, Jam.
Sir, please, like you're going very fast.
Oh, okay. Sorry about that. I will slow down.
Thank you very much.
Hamza,
Yes, please, sir. I want you to come back quickly about the unit weight. I
or the
want to know
unit.
what is it, yeah, what is it typically? Because it's a bit difficult for me to get it.
Hello, I can't quite hear you well. Can you please come again?
I want you to come back with the unit weight
All right.
to
So,
explain again, please.
okay, I'll do that. We are saying that the unit weight is the density of a substance influenced by gravity, right? And then we were saying that the density or the mass of a substance, even if you are in on moon or in any place that you find yourself, mass is the same. But the unit weight is the mass times the gravity over the volume. In other words, it is the weight that is being dissipated on a volume, right? Now, we all know that the volume is just a space, right? So the amount of weight that you are exerting in a given volume, that is what we are referring to as unit weight. So your weight that you are exerting on a given space that we have. Ah, please, did that make sense?
Yes, yes, please. Thank you.
You're welcome. So we saw that we have now established that soil is a three-phase system that comprises of solids, which the ones we see, water, sometimes we see, sometimes we do not, and then we have void spaces, right? Okay, now that we have that achieved, we want to move on to this. Now, this is the graphical representation of what I am talking about. So we have this stone here or a soil sample there, and then we are seeing that we are having the S particles, which are the solids that are so visible that we can see them. And then in between these visible particles, we are having water in between them. And then we are having air, which is also enclosed between these soil particles, right? So that is what I have been trying to explain, that a soil has these three components playing roles. All right. So now this thing that we saw here, this is what we, let's say, should I say hypothetically, that is what we can deduce from there. Now we are saying that that soil sample we saw in the previous slide has now been placed in this. And now we are taking our phase from the natural context so that to something that we can understand, so that we can make some calculations and some assumptions so that we can play with them and get to know, and then we can put error margins on the things that we cannot understand, right? So we have this container, and then we've put in soil inside, and then we've seen that this soil has water enclosed in it, and it has air in between the spaces, which is called the void spaces. Now, we cannot tell quite much from this point, so we try to put it in this phase diagram or phase relation. Now, we are moving from solid to liquid to air, so we are moving from one medium to another, so that is where the phase come in. Now, we can press this soil sample downwards so that we can compress it and have all the soil particles staying at one point. The moment we do that, and we have no void spaces in between the soil sample for the water to stay, then it would have to come out, right? So when it comes, it stays on top of the solid particles. And then after the soil have taken place, we also had some air instances within them. So it will also be filled on top of the water, right? You could also say that this thing is arranged based on densities, right? Soil is always denser than water, and water denser than air, right? So we try to draw this phase diagram from this soil sample so that we can assume things and make some calculations. All right. Now, we initially established that soils are either fully filled with water or partially filled with water. When it is fully filled with water, we are going to say something that it is fully saturated. All the spaces inside the water has been filled with a medium, right? And so when we have a soil sample as this, so this can be a clay sample where we took from a very waterlogged area, and then we brought it, we examined it, and then we saw that every space of the clay solid particles has been filled with water. And so we can deduce this from that point. Because we don't have air, we are getting two-phase relation, right? Two-phase relation. Right. Please, am I making sense? Am I going faster, or the pace is okay?
I think it's okay now.
Yeah, it's okay. It's perfect, sir.
For here, it's okay, but when you get to the calculation, you just slow down a bit.
All right. Okay. So we can have two instances of having two-phase water system. The first one being fully saturated with water. The second one dry without water, right? So we can, that same clay sample, and then we took all the water out, right? We placed it in an oven for about 24 hours, and then we heated to a temperature of about 105 degrees Celsius, and then we dried all the water from the sample, and then we had this only solids, and when we press them down, the volatile matter would want to escape, and then they are going to be at this point, having also a two-phased diagram, which is the oven dry. All right. Now, here we are, phase diagram. Right? So we try to divide, put some measures, use some jargons, put some formulas in order to understand what is going on with the soil sample. For example, for the purpose of study and analysis, right, it is convenient to represent soil by phase diagram because we cannot deduce anything from this messy structure that is there. You can't just find a point to take the area or the volume of anything there, right? With part of the diagram representing solid particles, right? And then we have parts representing water or liquid, right? And another part air or other gases, right? So we put them in this phase diagram. Now, I would want to explain what these things mean. Like we established that they are going to be divided into phases, and then we have the solid phase. The Vs here means the total volume that the solid is taken, right? And then we have VAT here, which is the total volume of the soil sample that we are working with, right? And then we have VV, which is the water part of the sample. And then we have VA, which is the volume part of the air of the sample. Now, we will know that the volume of air for every phase that we are going to consider here is approximately 0. So we are not going to bother ourselves with them, right? And then on the left side, we have the W's, which are the weights, right? So WT being the total weight, the VS being the weight of the solid. We have weight of water from WW, right? So the volume of water, the weight of the water, and then we have the weight of the air, which is approximately 0. So we are not going to be playing with the air parameter, right? Now, volumetric ratios. Now, we heard something from the properties, which is called void ratio, right? So the void ratio is the volume of the void over the volume of the solid. In other words, the amount of volume that we can have to the amount of solid particles that we have with the soil sample we are playing with. The amount of void that is inside the soil particle that we are playing with, right? So it comes with a formula which is VV, which is the part that is not filled with solid. So VV start from the air phase and the water phase, right? So VV over VS. So this point to this point over the soil part or the solid part, all right? Now we have porosity. Porosity playing with the void.
Hello?
Hello, Wisdom.
Yeah, please, good evening.
Please come again.
Good evening.
Good evening.
Yes, I just want to ask a question. I was having a network challenge, so I just joined. I want to ask a question. I don't know if I can go ahead.
Yeah, you can go ahead.
Yes, so with the void ratio, I know with void comes in a form of dimensionalness, meaning there's no dimension to that. So I want to ask, how do we quantify for that?
If I got you right, you are saying void ratio is dimensionless, right? And then you are asking how
Yes.
to is that? Hello?
Yes, so how do we quantify for that? Is it by maybe laboratory or like testing or something?
Okay. Yeah. We cannot in institute find a void ratio. We have to take the sample and go and check, break it into phases and see which part or which amount of this sample contains solid and the amount of the sample that contains air. And then it is dimensionless because we are playing with volume over volume. So even if we measure the voids and then we are getting, let's say, 5 grams per cubic centimeter, and then the solid is about 10 grams per cubic centimeter. But after performing our division, you will see that these guys are going to take off and it's going to be just a ratio. So that is why it is called a ratio. So the void is 1.5 of the solid. Please, are you getting it?
I get it. Meaning there's no unit to that because of the dimensionalist, right?
Yes, dimension analysis, the dimensions are going to also be operated and it's going to give us 1.
Thank you.
Isaac, please, I have a question.
All right.
Can I come in, please?
Yes, you can.
So we are talking about void ratio.
Okay.
I want to understand. So if you pick a sample of rock or soil, whatever, there's water in it.
Okay.
Does water form part of the void, or it is just the air component aspects that form part of the void? Because looking at this word, the void ratio, we are considering the air and the water. That's the VV, which has to do with the volume of air and water. But I know water, at least it fills spaces. I mean, at least you can tell that for air, that we can't really see. Will water form part of the void? I don't know if my question is clear.
Yes, your question is very clear. So with the void, the basic definition of void is space, right? Water can fill inside inside the soil component because there is space inside. Water cannot be compressed. It tends to fill any place that it finds spaces, right? So we can say that then there is water in this soil sample means that there are spaces inside the soil particle that the water can come and sit inside, right? That is why we are counting the void spaces with the air and the water, because these guys were able to get into the soil because there was space to occupy. Please, am I making sense?
So that means anything outside the solid is void.
It's void. Yes.
Okay, Crystal.
All right.
Thank you.
You're welcome. All right. So the void ratio is a ratio, right? So the ratio of this void spaces to the soil content that we have. All right. The second is porosity. Porosity. All right. Now the porosity is the volume of the void over the total volume of the soil sample. Now the porosity, which in other words can mean also spaces inside the water, right? But now we are want to quantify them with percentage, right? And then we are saying that it is the void, these voids that we have over the total water soil sample that we have, right? So porosity is the percentage of the void out of the total volume that we have, and then we want to quantify them with percentage. That's why we bring the 100%. All right. And then the third one is degree of saturation. How much or how far or how the degree means how to the extent of something is happening, right? That is degree. So how much or how extent of the void spaces in the soil sample has been filled with water. That is what we call degree of saturation. And then we want to put it in percentage. We want to measure, the soil sample we went to get from the site last week contains about 70% of water, right? So that is the extent of water that is filled in the soil sample, right? And then we are saying that the degree of saturation is the total volume of void which contains water over the total volume of the voids. Now, the voids that are present inside the soil sample, to what extent is it filled with water? Right? So that is what we are meaning by degree of saturation, right? We are playing with voids because we can only play with water when we have voids. If the density of the soil sample is so compact that there are no spaces, then water won't get a place to be sitting, right? So the degree of saturation will be 0. And that one, we can have a dry solid sample. And then when almost all the void spaces or all the void spaces are filled with water, we are having a saturated water sample. Soil sample, sorry. Okay. Now, we want to play with the ratios, right? And then when we are playing with the weight part, how we can manipulate things in order to get some further understanding with these phase relations, right? The first one that we are going to see is water content. Water content, which plays with something like the weight of water, right? So how much water is in a sample? when we take it and go and measure the water sample, are we getting 10 kg or are we getting, so we want to put the weight in percentage. So that is why we are saying that water content W%, right? So weight of water over the weight of the solids, right? So W over WS times 100, right? So please be paying attention to these weight ratios, and then after here, we're also going to see the volume ratios. Right. Okay. So soil unit weight. Now we've talked about unit weight, that it is the weight that can be contained in a given volume, right? And we are saying that gamma dry, which is the symbol of unit weight, gamma, right? So gamma dry, the weight of the dry solid over the total weight of the soil. If you want to find the unit weight, the amount of the dry sample or the weight of which the dry sample is going to exert on a given space, that is what we call the dry unit weight, right? So it is the weight of the solid soil solid over the total solid, the total soil. The second one is total wet, bulk, moist unit weight. Now, I want you to know that the total, the wet, the bulk, the moist all mean one thing. It is the total weight of the soil over the total volume of the soil, right? Now, if you could say then divided by gravity gives me density, you are right. So it is the total weight, the amount of force that they are going to exert to a given volume that you have. So we are going to say it is the weight of the solids, right, over or plus the weight of the water over the total volume. All right. And then we have gamma sat, which means that degree of saturation. Now, I want you to find some correlations with these two people. When saturation is 100%, bulk density and degree gamma unit weight. So we will see we also see bulk density, dry density. But I want you to know that gamma bulk or bulk unit weight is the same as gamma sat or saturated unit weight when the degree of water inside the solid is 100%. So these two guys are the same when the water content contained or the degree of saturation that is contained in the soil sample is 100%. All right. So it is the total weight of the soil over the total weight of the total volume of the soil. Yeah, wisdom.
So if it is 100%, it means all the void spaces are filled with water, right?
Exactly.
Okay, thank you.
You're welcome. Okay. So saturated unit weight, considering S is equal to 100%. So when S is equal to 100%, that means that it is full of water, right? And then if all right, Portia.
Okay. So let's say that it's not 100% and maybe it's 10%. That means can you use any of this formula to calculate it? Because it looks like the formulas are almost the same.
They're actually the same.
Yes. So in case it's not 100%, because you're saying if it's 100%, then this is equal to that, right?
Yes.
Unless I didn't understand what you said.
Yeah, that is what I said. So
So what if it's not 100?
okay. So look at something. We are saying that the weight of the solid plus water. Now, if it is not 100%, then we have to go and check the percentage of the water that is contained in the solid and add it. So with here, your water WW is not going to be the same as the WW here. So you have to find that percentage of water that is contained in that soil sample and add it at this point. Please, am I making sense?
Yes. So that means you would use the second
Oh,
formula. What if you want to still use it in the first one? Maybe there is 10%. You still have to the gamma without the gamma, another gamma with
okay. When you were
saturation.
talking, your voice was breaking, but I got what you said. So if
Clear
it is
with my
10%, then you would have to find this
question.
water, the weight of this water portion, and use it. Well, since they are the same, you wouldn't know if you are using this one or not. They are the same, but you have to keep it in mind that you have a percentage that you are going to